Okay, hello. Hello, everyone. How are you this afternoon? I hope you're not tired because we got quite a lot to do. So let's actually begin. What you can see on the screen right now is a typical answer for a pretty common C#.NET interview question, namely where are stored objects, where are stored value types, and where are stored reference types in .NET platform. And typical answer is value types are on the stack, reference types are on the heap. You could say that, you could answer it in this way, and this would be probably right. However, throughout this talk, what we are going to do is we'll discuss whether this question is actually good, whether it does make sense to ask a question like this, and whether we can bend the rules and somehow modify the default allocator in .NET and allocate objects wherever we want. So my name is Adam Furmanek, and I'd like to welcome you to this presentation and invite you to the world of unsafe, where we are going to actually do a lot of low-level nice tricks around the memory allocation, allocate objects on stack or anywhere else, implement custom data structures performing better than list of T distributed with .NET, and do some more hijacking. Before we actually begin, a few words about me. I was a .NET developer for over 5 years. Now I'm more of a big data, Scala, machine learning guy at Amazon. I'm a blogger, public speaker. Feel free to drop me a line on Twitter and take a look at my blog. This whole presentation is on my blog. Also, there are quite a few more posts describing the things I'm going to show you today. So feel free to take a look afterwards if you are interested. Okay, agenda of this talk. So because what we are going to do is we'll actually implement custom memory allocation mechanism in .NET. We'll allocate reference types on a stack. We'll actually allocate objects anywhere we like. We'll hijack new operator in .NET to reroute the allocation mechanism to use our own code. So in order to do all of these things, what we need to start with is the details of how it works under the hood. So we'll take a look at the memory structure, at the allocation mechanisms and primitives which are there in .NET, and we'll see some magical keywords which are, for instance, not recognized by ReSharper, but still available in .NET since .NET version 1. Then, what we are going to do is we will see a lot of demos showing what we are actually modifying. We'll see some machine code, some intermediate language as well. We'll debug some memory and work with WinDBG. And all of that just to allocate objects using new operator and hijack this operator to use it the way we would like. So let's begin. We started with a question, where are objects stored in .NET? And if we take a look at the .NET ECMA standard, it actually does not enforce that the reference types must be stored on a heap. It's typically that they are stored on a heap, but it does not require that. Actually, there are operating systems out there which do not have heap at all. So if we would like to implement .NET for those operating systems, we need to somehow either implement the heap on our own or actually go with stack allocation all the way down. Also, when it comes to value types, we know that they are stored on a stack, like by default. However, if a value type is a part of a reference type, like integer is a field of a class, it's stored on a heap as well. So generally, value types can be stored anywhere in .NET, and this is by design. The question is, how can we allocate .NET reference type on a stack? This is not something we can do by default. There were proposed add-ons to Roslyn or to .NET Platform to be able to allocate objects on a stack. There is ongoing work in .NET Core to support escape analysis to move reference types to the stack where it's possible. However, as of now, we cannot do this by default, but we are going to do this in this talk. So the thing about standard is, it does not require that the reference types are allocated on a heap. So now the question is asking where are value types or reference types stored enough? Maybe we should instead ask the question like, where are they stored in .NET Framework version this, in Windows version this, on architecture version this, using patch version this, blah, 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 to specify which implementation are we actually talking about. But then if we ask this question during interview, this is probably the answer we'll get. Because who cares? Why ever we should ask all those specific details about the platform we are using? Because on one hand, it's good to know how it works under the hood. On the other hand, it's not very, very required in day-to-day work, especially in business line applications. So this was just a digression, like university scientific one. Let's now go to the internals. Whenever we have a new object, what we used to say is when we have a line var o equals new object, we say that o is our object. And this is not true. In this talk, we need to be a bit more specific, and we need to have this differentiation between a reference and an object. The object is on the right side of this equation. Var o is just a reference pointing to the object. So objects are allocated on a heap, but what we hold in the variable o on the slide is actually a managed pointer which points to the object, which on this slide is marked as this rectangle in the middle. This is our object, but o is just this pointer. The size of this pointer depends on the architecture. It can be 4 bytes, 8 bytes, whatever else, depending on the architecture. And the thing about the object is that it stores the data, only the data, no methods. Methods are stored somewhere completely different, and we'll actually take a look later how methods are stored in .NET. But with object instances, what we only have the data, so the fields describing the actual things we store in the objects. But there are two more things related with every object. Actually, we know there is a thing called reflection in .NET, so we can ask the object, hey, which type are you? What are you, basically? And this works in runtime. It's not compiled time. It's not during the compilation. It must be realized and performed when running the application. So every object must have a tag, which is called in .NET world actually like execution engine class or type handle, or runtime type information, just like here, RTTI. There are multiple names explaining exactly the same thing. There is a tag related to an object associated with the object, so the object knows what it is. And actually, our reference is pointing to this tag, to this RTTI address. And on the right side of this slide, what we have is the description of the object, which we can use during runtime using reflection to actually figure out all the details of the object. So which methods it has, which field it has, properties, interfaces, inheritance hierarchy, everything else. Everything is stored there. So thanks to that, in runtime, we can ask the object, give me your tag, and then we can figure out the type of this object. We cannot do this with value types, because value types do not have RTTI address. They do not have this execution engine class associated, so the only thing we know about value types is just some value. We don't know the type. One might ask how it's actually possible to call getType on value type in .NET then. The answer is boxing. Whenever we box a value type, we actually have a separate class describing this is boxed integer or boxed double or whatever else. But there is one more thing. One more thing with every object, which we can see actually here. This is the sync_block address, which is one integer just before the RTTI of the object, just before the type of the object. This thing is used to store details about like hash code or locking mechanisms or some metadata of the object if they are pre-computed, or if this data is too big, it's just an address pointer to some other metadata associated with this object. What is interesting here, it's actually before the object. Whenever we take a look at the pointer, it points to the middle of the object, not to the sync block. The sync block is effectively physically stored one integer before the object. So this is how it works under the hood. This is our object. What we are going to do is, our main goal for now is to allocate this thing on a stack. We want to do this. So we need to now figure out what we want to allocate on the stack. So there are three things we would like to allocate: sync block address, RTTI of the object, and all the fields it has. Those things we need to allocate on a stack, and then we need to somehow grab a reference to this object while it's on a stack. And to do this, what we are going to do is we'll use the keyword, which is unknown to ReSharper, and which is there since .NET 1, and namely it's makeref. This is an excerpt from MSD and documentation, what this keyword does. It's actually a bit tricky because what makeref returns is a typed reference, which sounds very similar to a reference, but it's completely different. Typed reference is a reference to a reference. So it's pointer to pointer. Thanks to this instruction, we could get a pointer to the object. And using this pointer to pointer, we can modify the original reference to reroute it to somewhere else. There is also another keyword which is called refValue, which does the opposite. We give it the pointer to the object, and it returns us the reference to the object, which is effectively a pointer. So those things we are going to use, and if you are lost how it works under the hood, beware no more, because there is yet another pointer going on. Because we cannot just use typed reference, because we have type safety. What we need to do is we need to get a pointer to a pointer to a pointer to the object, so we can then treat it as an integer and then modify everything else. So once again, we have a new object. We start on the left side here. New object is on a heap somewhere. It holds some value here depicted as 65, yes? Some value. Then we have a reference, normal C# reference, nothing new here, which we call object O. This is just a pointer which has a value 5000 because it points to the object which is stored at the address 5000. Then we get a pointer to the object, which is typed reference, which we get with __ makeref. This is pointer with value 6000, as our reference was at address 6000 pointing to the address 5000. I'm speaking as fast as I can just to make a lot of more confusion here, but then we get yet another pointer. So we get the pointer to the pointer to the pointer to the object. I hope you get the idea. I know it's a bit tricky, but with the code, it's getting much easier. So let's actually see the code. But before we see the code, we would like to make sure that, hey, we know what we are doing and we are actually convinced that we are doing what we want to do. So few GC facts, garbage collector facts. So there are 3 generations in .NET Framework. I'll be using .NET Framework throughout this talk, namely generation 0, 1, and 2. There is a thing called large object heap, which stores objects which are at least 85,000 bytes long. So either very big objects or like big arrays, etc. Also, there is a very nice use case. 1,000 array with 1,000 doubles is also stored in large object heap, like a fun fact. And large object heap is in generation 2. We are going to use this fact to figure out actually whether our objects are stored where we want them to be allocated or not. And trivia for you, just before we actually go to the code, is which generation is a stack? You probably know you can call gc get generation, and it returns you which generation is this object in. The question is, what is it going to tell us when we ask for an object which is stored on a stack? Let's begin. So, first demo. And what we are going to do is, we are going to cheat just a little, because we are not going to allocate the object on a stack yet. What we are going to do is we'll just copy the object to the stack. Later, in one of the later demos, we'll be able to allocate objects from scratch. But as for now, we'll just make it a little simpler. So let's begin. We have this very simple class Poco, which has one integer field with one non-virtual method called writeField, with one virtual override toString, and with some destructor. Yes, nothing fancy here. What we want to do is we create a new object here, which is allocated on a heap. Is that correct? That's correct. Then we create another reference pointing to the same object. So we'll have 2 references pointing to one object on a heap. Then what we are going to do is we'll allocate some memory on a stack, initialize it to bat food literal, just to be able to see this literal in the debugger to see that we are looking at the correct memory. And then what we are doing here is we are doing some pointer magic. Just like I said, what we are doing here is we start with our heap Poco. This is a pointer to an object. Then we get a pointer to this pointer using makeref. So now we have pointer to the object. Then what we do is we get address of this, effectively getting yet another pointer. So pointer to the pointer to the pointer to the object. Now what we can do is we can cast those things to pointers to integers, just to trick the compiler. So type safety is that we can just compile this code. It doesn't scream about wrong types here. So we just dereference those, cast to integer pointers, etc. We subtract 4. That's because I told you the sync block is before the object, and it's one integer, which on my platform, because I'm compiling this on any CPU, is 4 bytes long. So we need to subtract 4 bytes, and then we have a pointer which actually points to the very beginning of the object. And then we print things like the RTTI address and some other things, and we just wait here in readline. So let's start it. So it printed out something. And what we are going to do right now is we will launch WinDBG, attach to the process. For those of you who are not familiar with this tool, in Windows, there is a debugging engine installed directly in the operating system. You don't need to install anything, and especially with Visual Studio is not installing anything for you just to make the debugging possible. It's possible there always. What you need to do to be able to debug something is you need to have some form of an interface on top of this debugging engine. Visual Studio is one interface. There are many more. For instance, there is .NET Spy. There is WinDBG, there are some console debuggers, things which you can use just to start your debugging session. The thing is, why am I using WinDBG instead of Visual Studio, is that there is an extension distributed with .NET Framework, which is called SOS, which is Son of Strike. This extension is able to read the raw byte structure of your application and show it to you, something which you could do in Visual Studio, I think, until 2012, which is not possible anymore. So what I'm doing is I'm using exactly the same debugging engine which you are using with Visual Studio. It's just some different UI because I'm using some different extensions to the engine. So first thing I'm going to do is I'm loading the plugin, the sauce, allowing me to read the memory. Then I change my thread. And then what I'm going to do is actually I want to dump the whole stack and everything there. Let's make this hopefully a bit bigger. But yeah, now a bit better. Is this readable at the end? Yeah, cool. OK. What we got here is I started this application, and we are now in this line, console read line. So what we can see here is, yes, we do have our call stack. This is program main. This is read line, read line. If we scroll to the right, we should actually know we do not see the lines here. We do not. But OK, let's just assume that I'm telling you the truth. But you can see that read line is here, so it looks like this is correct. So what I have here is all the objects, everything which is there in memory. And you can see things here which are allocated. So I have heap Poco, and I do have original Poco. So I do have those two variables, those two references pointing to the same object. And as you can see here, addresses here are the same, because they point to the same object. So what I can do right now, I can just dump this object, and you can see that it has one field with value which is given here, which is value 5. So you can see exactly the same thing I allocated here. So we do have value 5. And also, you can see the address of this object is here, and the method table, so RTTI address, is here. So RTTI ends with DB4, and object is 838. If we now go here and take a look at the output of our application, we can see that E method and value is exactly the same. Yes, this pointer may be 4 bytes earlier just because of the sync block. But we are actually looking at the correct data. So what we want to do now is we want to copy this object to the stack. Let's see our stack here. When I dump the address of our stack frame, you can see 10 bad food literals. I told you we are allocating some bad food on a stack just to see this memory in debugger. This is what we are looking at. So far, so good. Let's carry on. So I just resumed this application and hit enter. And what our application is now doing is it's going to copy the object to the stack. So what it does, it uses this magical Poco address variable. So we read the bytes, we print them out, and we allocate them in this array, which we allocated on the stack. So we are just copying 3 integers. Why 3 integers? 1 sync block, 1 RTTI address, and 1 field of the object, which is just the only integer we have in our Poco class, which is here. So we are copying 3 integers to the stack, and now we can, since we have done it already, what we can do is we can break in the application, in our debugger, and try to dump the stack again. And this time you see that 3 bad food literals are gone. Now we copied 3 values, and oddly enough, this thing is exactly the thing we saw in the output. This is our RTTI address. So now we have a proper object on a stack. Those 3 integers are the object. What we now want to do is we need to grab a reference to this object, so we can use this normally. So we resume our application again, we hit enter here, and what we are doing in this line, in this line, we set the reference which was originally there, so it points to the address which is inside the array stored on the stack. How it works, we do have our typed reference, which we created using makeref. So we just need to get this pointer to pointer to pointer to object, but instead of going all the indirection levels, we just need to go from pointer to the pointer to the pointer to the pointer, and modify that one value. Because this is reference pointing to the heap, we'll just reroute it to the stack. So believe it or not, this is what we are actually doing here with these magical pointer operations. What we can do now is we can break again, and what we would like to do, we would like to change the thread again and dump the stack with all the variables again. And now what we see here, those 2 values are different. Because our original POCO still points to the heap, but our heap POCO our heap POCO is very close to this value. And this value is actually the beginning of our stack frame in this method. So we modified this one reference, and now we have a reference pointing to the object on stack. So we can resume our application. And actually, what we could do as well is we can create a stack POCO using this ref value keyword, which is redundant here. We don't need to create a new reference, but if you would like to go with ref value, this is the way to go. So now what we would like to do is we have our object on the stack. We would like this object to be normal, ordinary object working the same way as the object on a heap. So what we would like it to be able to do, we would like to be able to read and write fields, to call static, virtual, non-virtual methods. We would like it to be we would like to lock the object, so use the sync block correctly as well. So now we are just testing whether things work here. So what we do is we just print the field, and we call non-virtual method from the original POCO and the stack POCO. So let me just hit enter here. So originally the value was 5. We copied this value to the stack. We can see 5 here, 5 there. Then when we modify those fields on a heap on the stack to 3 5s, 3 4s, we print them out again. It's exactly the same. And to convince you even more that this object is on the stack, we can modify it just by modifying values in this array of integers which was allocated on the stack. So we know this field is at the index 2, we modify this field, and yes, the object was modified. Then we would like to actually be able to call virtual methods, which is toString here. So we just call toString, and toString in my implementation is very simple because it just returns field toString. So whenever we do this, we should actually see the same field again. So we have 3 5s, 3 times 3. Then we display object types, just to make sure that the RTTI reflection, everything around works correctly. And we can see makeref POCO. This is my POCO class, so it's the same. And ultimately, we would like our locking to work correctly, so we would like to be able to modify sync block. So I have 2 tasks. One of them will lock stack POCO. Then other task will try to lock the same object, but there will be some timeout here for 2 seconds. So when I hit enter here, oh, sorry, I just missed generation. Answering the trivia, where is stack? Stack is in generation 2. Why is that? Because it's implementation detail that whatever address, .NET checks the addresses. If the address is in generation 0, actually .NET tries to check the boundaries. It knows where the generation 0 is. So it checks the boundaries. Because the object is not in generation 0, it checks the boundaries for generation 1. Since the object is not in generation 1, by default it must be in generation 2. We just only hacked this a little bit, so it's actually like a side effect, not something they explicitly encoded, but this is how it works. And returning to this locking, so I hit enter again, and you can see that I'm taking some locks, and then after 2 seconds, locks are released, taken again, etc. So it looks like the object works correctly. And ultimately, what we could do is we could just register the object for finalization, so it's cleaned up by the garbage collector. I'm not doing this here because this thing crashes pretty often as we are releasing object which is on the stack, so the stack may not be available there. So let's just recompile this and see how it goes this time. Last time it unfortunately crashed, so hopefully this time it works again. So let's just few seconds until it compiles. With this Visual Studio working in virtual machine, which makes it even slower than typically. And let's go through this application again. So now logs, and we hit enter. No, this time it did not crash. So you can see that garbage collector actually called the destructor, and the object was cleaned up. But generally, you should not be doing this, as this may crash your application. Cool. So raise your hands if you are convinced. We allocated object on stack. Yes, I can see some hands in the air. Cool, because right now what we are going to do is we are going to do even more fancy things. So generally, you know how list of t works in .NET. It works not by storing the objects, it stores the references. So in C++ world, it would be something like vector of shard pointers or whatever pointers are now fashionable there, but it just stores the references. So whenever we would like to iterate through these objects, so what we do is we go to reference, object, reference, object, reference, object. So we have this ping pong style. What we are going to do is we'll implement list which stores the object inside its content. So when iterating through the list, we'll not do the ping pong, we'll just go object, object, object linearly. The working hypothesis here is if we allocate objects next to each other, during iteration, we should do it faster than list of t. Why? Because of CPU caches, etc., etc. So let's actually see what we are doing and how it works. So let me just close this demo, open yet another one. Okay, and I'll start it in the background and explain you what it does. So we have a Poco class with 16 integers. And what we are going to do is we'll test 3 collections: array, list of t, and our unsafe list. So for each test, we actually generate a Poco with some values which depend on the iteration. And then when testing array in this example, we create an array of objects, we create Pocos, allocate them, we measure this with stopwatch and print the insertion time at the end. We reset the stopwatch, and then we iterate over objects and calculate the sum of all the fields. And then stop the stopwatch, print the result, print the time. We do the same for list of t. We pre-allocate the list with the elements so we do not spend time or reallocating the list. And ultimately, we do the same with unsafe list. And my test is being run 3 times for each collection with 20 million elements. Even though it says debug here, it's running in release, just this one project. And also, since this is running in virtual machine, results might be a little skewed. But you can find in my blog a post actually measuring this with benchmark.net and confirming that this tends to be faster in some cases. And few more things about unsafe list. What we do here is we have an array of integers which we use for storing our objects. So we need to accept the size of the array, how many elements we would like to allocate, and how big every element is. And then when adding, we do the same magic with makeref, pointers to pointers to pointers, copy things. And then we also prepare a reference pointing to this object, and we store it in our array, helper array here, so we do not need to recalculate this reference every time when we try to access the object. So what we have as a result, so you can see that first we are going with array. Insertion time is something between 4 and 8. Generally, this is typically around 4.5 seconds. Iteration time is around 200 milliseconds. Typically, here it's a little lower, apparently. For list, we can see that list has very similar results, around 4 seconds. But what we can see for unsafe list is that insertion is almost 3 times faster. So first, And also, iteration is very similar to list of t and to a normal array. So what we can see is our working hypothesis was not confirmed. Iteration was not faster with our unsafe list, but insertion was faster, which is actually very interesting, since now instead of storing just one reference when adding an object to a list, what we do is we copy like 60-something bytes to the list. And still, it's much faster. So I encourage you to run experiments on your machines to confirm those results or see that they are different. Actually, this demo is based on a demo which was created in Java world. There was a blogger who implemented a very similar thing in JVM, because in JVM you also can allocate memory the way you like, anywhere you like. And there, this working hypothesis that iteration through object is faster was confirmed. Then there, the guy got results showing that iterating is faster, whereas adding items to a list is much slower. Here I get some different results. So this is actually interesting. If you are interested how it works under the hood, you can decompile the code and see some machine code like this to figure out whether there is a vectorization or whatever else. But we can skip this, omit this for now. So that was demo number 2. So in first demo, we allocated object on a stack. What we actually did, even though we did not emphasize this, is we allocated the object anywhere we wanted. Anywhere. It's not that we need to allocate it on a stack. We can allocate it anywhere we like. So in demo 2, we use this to implement this list. Now, the next step is actually to implement a full-blown normal memory allocator in Dotnet. This is the thing which we are going to do now. So what we are going to do is, let me just close things here, and let me just set us start up yet another demo and run it. So I told you in first demo that we allocate object on a stack, which was not true actually. We were just copying the object to the stack. What we would like to do is we would like to be able to create this object from scratch and also have some compiler support when doing that. Yes, we do not want to run in this unsafe world constantly. So what I would like to do is, whenever I have this object showing all the possible things, primitives, enums, etc., I would like to allocate it in this way. Because I cannot just call new object and pass the constructor parameters, because I don't use new in my case, what I would like to do is I suggest we can use an expression here. Instead of creating this object and then copying it, we just describe how to create the object using expression of func of the type we would like to allocate, and then pass all the parameters here. Thanks to that, we can later examine this expression, evaluate all the arguments, and allocate the object the way we would like. So what we are actually doing here, just showing you that this object is created and it has all the values, and we can also deallocate it using by calling our allocator explicitly. The only thing which we didn't know in demo 1 is how big the object is and what is the RTTI, what is the type handle of this object. So what we are actually doing in our allocator, to get a type handle, to get RTTI address, this is actually pretty easy. We can just go with reflection, get type handle.value, and this is it. So we want to allocate this object, and now we have the type handle, so we know how to allocate the type of this object. But to get the object size, what we need to do is we actually need to rely on some details of how the objects, how the metadata is stored under the hood. So if you decompile the code or go with debugger, you can actually see that the size of the object is stored around here. So you just get the type handle, which is pointer to the metadata of the object. You need to read one integer, which is 4 or 8 bytes after the beginning, and this is your size. This is just the integer. So we do this, and then what we do is we can implement the allocator any way we like, any way we are used to, like when writing in C. So we can go with simple implementation of free lists. So we get a free chunk of the memory, then we allocate this chunk. If we don't have available memory right now, we create new object, we remove it from calling the destructor just to be a little safer. We also pin the object so it's not moved by the garbage collector, otherwise our references would be broken, and we store the chunks, etc., etc. The last thing which we need to do is we would like to call a constructor. Yes? How to do it? So actually, to call a constructor, let me just figure out where the constructor is called. We can go two ways. Either we go with reflection. Actually, you can call a constructor for an object multiple times with reflection. You can also create objects without calling a constructor. That's like another digression. So either we go with reflection, or we can go with a code calling the constructor but generating intermediate language code. Yes? So what we do is we create a dynamic method, we emit, we get IO generator, we emit all the opcodes to actually evaluate the arguments. If the arguments are value type, we need to unbox them, and then we just call the constructor and we return the object. That's all we need to do, and this actually works under the hood, and we can allocate the object anywhere we like and play with any allocator implementations we would like. Yes, so we can go with free list or with different allocation policies like best bet or lowest chunk, etc., etc. That's it. That's it when it comes to demo number 3. So now we can see that we have a full-blown allocator. So we are happy now, but there is just one thing which really irritates us. We need to write this expression tree. We need to pass this lambda to create the object. What we would like to do actually is we would like to say new something and get this something allocated the way we like and in the place we like. So let's actually see what does this new operator does under the hood. So when you go to documentation, what you can see here is that new object, which is actually instruction called by the new operator in C#, it allocates a new instance of the class associated with constructor. Constructor here is actually a type handle which we pass. So we pass the type describing what we want to allocate, and then it's used to create the object and call it constructor. It also initializes all the fields to 0, etc., and calls the constructor the proper constructor. So what we have is exactly the same what we did in demo number 3. We had some free chunk of memory, which was zeroed somewhere before getting it. So we allocate the type handle of the object. So we store the type of our instance which we are allocating. We call the constructor, and then we return the reference to this object. So it happens that we are actually doing exactly the same thing as the new object instruction is doing under the hood. So the last missing bit here is how to convince new object to call our code instead of allocate memory it used to do. So before getting to all those things, we will do it manually. So let me just prepare my last demo and set it as start a project. What we are going to do here is we will use the allocator we wrote in previous demo. And what we are going to do is first, we allocate the object using this allocator just to make sure that the object is in generation 2. So we know it's allocated by this allocator, not by the normal new thing. And it's allocated in the place we would like it to be. Then we create new object, just normal ordinary new object. We hijack new operator, and we allocate yet another object. The expected output of this, when we print out all the generations for the objects, is when we run this, first allocator should be in generation 0, because this is in line 167. This is just a normal object allocated in generation 0, yes? Then we allocate object using our allocator. This object should go to generation 2. Then we allocate 2 normal objects using new operator. First of them should be allocated in generation 0, and the latter should be allocated in generation 2 after we hijack the new operator. Since the hijacking is commented out here, both of them are allocated in generation 0 right now. But what we can do if we uncomment this thing and recompile this code, the difference right now should be actually in this line, because when we now hijack the new operator, you can see that the last object is allocated by our allocator in generation 2. And the only thing we did was hijacking the new operator. Let's comment this out and do this by hand. So let me start this up, recompile this application and start it again. It's now waiting in this read line, in this line, just before allocating last object. What we are going to do is we are going to use WinDBG again to see actually what happens under the hood. So first, let's load source. And then what we would like to do is I would like to decompile this main method to see what machine code is running under the hood. What is happening there? So I do have a cheat sheet here to copy the commands to actually find the object where it is, or actually the metadata of this method. So what it prints out here, it shows that the method is in this assembly, this module. The method name is program.main, and the JIT code of this method is here. So let's now decompile this code. And you can see this is normal machine code, no assembly, no C, no intermediate language. What we are doing here is we are looking at the normal machine code, raw bytes. So what we want to do is we would like to see what is happening in this line. Yes, in line 171, we do have lines printed out here, so we can see that line 171 is compiled to this part. And this part, because it's not very readable, I will show it to you using slides. So what we do here is we are actually doing the things which new object documentation told us to do. So first, we move to ECX address, we move there the type of the object we would like to allocate. This is this constructor which was mentioned by the documentation. And then what we do is we call .NET helper code Corinne for help news fast here. When we get the output, which is returned to us in EAX register, we just store it somewhere, and then we call the constructor of this object. Yes? So calling the constructor is this part. Allocating is the first two lines. So what we would like to do here is when we go back to our code, what we would like to do is we would like to get this address and see what it does under the hood. I will show you this code once again on the slides, but before that, let's just write this address as .NET Allocator method so we know where it was. So let's go back to slides. When we decompile this code, what it does, it just does exactly the same things as we did in demo 3. So first, it just gets the free chunk of memory and checks how many bytes there are still available in this chunk of memory. So it gets the object size. When you imagine a chunk of memory, there is a pointer pointing somewhere in the middle saying that I used this beginning of this chunk, and this part of this chunk is still available to me. So I just get this pointer, add the size, and then I check whether I moved out of this chunk or not. If I did not, then I can just, it means that the object fits here, it can be allocated here. So what we actually do is we do some bookkeeping, we update the pointer to the last byte allocated, we calculate the begin address of the object, and we just return it. But if we jumped out of this free chunk, then we actually need to call the last line here, which is JIT_new, which is like a proper method going to operating system. Hey, I need some more memory, please give me, etc., and then allocate the object. What we would like to do is we would like to replace this first part of this method. And instead of allocating it in the chunks which .NET knows about, we would like to allocate them using our allocator. So let's go to the code. And oddly enough, you may say, actually, I do have a method which is very similar to the method which .NET calls. Very similar in terms of method signature. How we were calling the method in .NET, if you take a look here, is we just pass one parameter through ECX address. This is the type of the object we would like to allocate. So you can see that I have a method which is static and accepts exactly one parameter. Why is it static? How many parameters would this method have if it was not static? 2, because it would get implicit this pointer. Because we do not want this parameter, it's static, so we get one pointer and we return exactly one pointer. So the signature matches the method we would like to do. What we do next is we just get the object size etc., do some magic with makeref, with pointers, we allocate this object, and we are done. So the thing is how to convince Dotnet to call this method instead of the original one. And we can do this by modifying the machine code. So what we need to do is, let's figure out where our method is in the memory. So if I run this command, what you can see is that my allocate method is at this address. If I now dump this method, you can see it has lines around 89, 91. So if we go to 89, it's actually here. Yeah, this is the method which we are looking at right now. So we can also see that this is our method for allocation. What we can do right now, let's modify the original method. Let's modify the .NET method. So I am now in the machine code modification mode, and what I want to do is I would like to modify first line of the .NET method and do jump. Sorry for that. Let me make this a little bigger. What I would like to do is I would like to do the jump to our method. So I modify the code. Sorry for that, syntax error. And now I exited this mode, and my application probably crashed. I need to enter this modification mode again, modify it with this address, and I'm done. Let's now decompile the .NET method again, just to make sure that we modified it correctly. And yes, if we now take a look at this code, which we marked as the .NET method, we can see the jump is here. And we are jumping to address E0, which is here. So it looks like we are all good. Assuming I did not make any typos here, etc., when I now hit enter in this, you can see that yes, in fact, we allocated this object in generation 2. What we did is we just jumped from the .NET code to our allocator, returned the object, and we are good to go. This is how we did it, but we did it manually. Let's now do this automatically. So what I'm going to do is I am actually going to uncomment this line, run this application, and it's still waiting in this read line. Yes, what I would like to do is I would like to attach to this process to generic unsafe alloc, and what I would like to do is I want to show you that hey, this actually works the way I explained you. So I'm hitting what? Hitting enter here. We are now in this line new object. I add a breakpoint here to go to this console write line, and I also add a breakpoint here. If the operator was not hijacked, we would just go to line 179, yes? So now I hit continue, and we are in our raw allocate method. We can also see with our call stack that we came from new object to our method here. But that's not enough. If I hit continue again, I add breakpoint here to the next console write line method execution. When I hit continue, we are in raw allocate again. Why is that? Because in this line, we are actually concatenating some strings. So we do allocate new object. So all the allocated objects are actually going through our allocator. So when I hit continue a few more times, you can actually see that I'm still in our allocate method. And there is some external code here because I do have enable just my code. So it's not showing me the .NET internals under the hood. So it looks like it's working. Now the question is how it works. And the hijack part is actually pretty easy. We do the same things we did manually. So we have a very simple method which is not inlined by the just-in-time compiler. We just create a new object. What I do next is I get the method of the address of this method. I JIT compile it, so it's available. And then I know where the call to the .NET method is actually inside the machine code. So I know the offset. This code is prepared just for my architecture and debug and release mode. If you would like to use this in different architectures, like 64-bit architecture, ARM architecture, etc., you need to add some if and if here, just to make it, just to support more architectures. What we do next is, because we know the address of the .NET method, we know the address of our method, what we actually need to do is when we return the address, we need to generate a piece of machine code. This is one level lower than the assembly code because we need to also take care of which jump instruction we are actually using. So we generate few bytes actually performing the jump, the relative short jump with this offset, with these addresses. We store those bytes in memory, modifying the original .NET method, and we are good to go. And having said all of that, that would be actually it. There is a QR code pointing to my blog series explaining all those things. You can also find those slides there, so if you want, feel free to just scan this code. There are also some more posts explaining how to actually implement Allocator, which works by allocating on a stack using FODI and rewriting the assembly code under the hood, and a lot of more interesting things about manual memory management, .NET internals, etc., etc. Questions? Do you have any questions? Here was first question, please. Cool. The question is, how does the new span in .NET Core fit here? Actually, what I did is you can do very similar things with span, and it looks like span is exactly the same things I'm doing here, but they are just safe. Compiler knows what you are trying to do, so it tries to stop you when you break things. Because I'm just generating machine code like by hand, this is unsafe, as the title suggests. It can crash. And actually, when preparing those demos, it crashed pretty often. It's only now which is working nice. But with span, you get the advantages of what I've shown here, but you have much better type safety. So actually, very similar ideas. And also, I believe here this last link on this slide is pointing to a Roslyn stack alloc proposal, which was there like 4 years ago, which was actually trying to do what I did just automatically by the compiler. So generally, those things align. You only get better type safety. Another question. Yes? Got it. So the question is basically, where would we like to use this so it's safe, it does not crash, and it's actually better? It is used a lot, and actually it's related to those span of T things in game development, in image processing, in video streaming, etc. In those areas, you pretty often need to actually go and read the memory directly using pointers to not copy bytes here and there. To do that, previously, you had to use things like this. Actually, one might ask, why even bother with this makeref? What is this keyword doing in .NET at all? Before we had generics, whenever you passed a value type to a method which was supposed to accept anything, you got boxing. So to avoid the boxing, you could go with typed references to read the objects directly. Since we have generics right now, we do not have boxing. This use case is not like very common anymore, but also at that time, it was exactly the same. You wanted to get some performance boost just by avoiding copying of the memory here and there. This is the same with span. You can use span to read the memory directly. It's only slightly better because of type safety. So wherever you actually want to process some data with and avoid redundant copies, there it's actually a place for those things, and there they are actually used. I know there is one big company working on some queuing system which is using things like that to manage the memory directly and to allocate objects directly. So yeah, this is not something which is not used at all. Probably when you use this, you may want to go with C++ and do some p invokes. But if you want to stick with C#, you can do this easily with just unsafe and pointers, etc. Any more questions? Yes. Which part exactly? Cool. What we did in demo 1 is we just copied the object. If you would use the same, you would do the shallow copy, not the deep copy, shallow copy. Would it work if some other code would allocate objects? Yes, because we modified the new allocation mechanism, it would work. Would the garbage collector clean up the objects properly? If you have nested objects, some of them allocated by Dotnet, some of them allocated by you, this probably would not work because I'm just freeing only the objects I allocated. But for all the other objects, GC should clean them up at the right moment sometimes in the future. So I would generally say like 95% it should work. I did not test this extensively. It may be crashing in some scenarios, but generally, yes, this should work. Any more questions? If there are no more questions, feel free to, I'll be wandering around here, so you can talk to me after this talk. And some more references for you. If you are interested in .NET internals of any type, those are books which I highly recommend reading, starting with going from top to the bottom, like from the highest low level to the lowest low level. You can start with CLR via C#. It's like a you could say elementary book about low level, and then actually what you need to do is read more and more about Windows operating system internals, so Windows via C++, Windows internals, etc. If you want to know how to use WinDBG, how to either read the memory I did throughout this talk, or how to track memory leaks or deadlocks, etc., WinDBG is a great tool for doing that. There are 2 books by Mario Hewart, and I think there are also 2 Pluralsight courses with the same titles, namely Advanced Windows Debugging and Advanced .NET Debugging. If you would like to go with like customizing the .NET, I mean change the way how it allocates the memory, how it creates the thread, etc., you can do this by modifying the shim which creates .NET process for you, and this is nicely described as customizing the Microsoft CLR. If you are also interested in like .NET internals of memory structure, of how it manages the memory, etc., everything around that, there are 2 nice books. Shared source CLI, which describes the project Rotor, which is actually open source .NET 10 years ago for research purposes, and also Book of the Runtime. If you're interested in all the memory under the hood, Expert.NET IL Assembler, great book explaining all the single bits of memory. And generally, if you like those low-level things, maybe just to read about them, not necessarily use in your applications, great blog, The Old New Thing, where when Raymond Chen explains all the architectures, debugging, etc. If you're interested in things I did throughout this talk, here are some links pointing to allocators, to hijacking new, hijacking any functions in .NET, etc., or running machine codes. And if you are finally interested, just waiting for a few people to capture their photos. And if you are interested in like the allocation, which I told you generally, there's some nice materials as well, like debugging demos or .NET memory structure, or playing with unsafe in JVM. This is actually the unsafe list in JVM world, which I mentioned, make ref, stack alloc, etc. All those things. Just as I said, those slides are on my blog, so you can find them there. And yeah, I think that would be it. Having said all of that, I think it's time to call it a day. My name is Adam Furmanek, and I'd like to thank you for attending this talk. I hope you enjoyed it. Thank you.